All right, in the last three examples, we have derived the general equation using variables, using numbers, seeing fractions, and now we're going to do it for the formula, like the one that works for every single geometric sequence ever. In order to do that, it does look a little bit funky because we do not know how many terms this formula will have because we're doing the general formula for n number of terms. So it looks a little bit funky. Stick with me. We've got this. We are just going to follow the same steps. We're going to look for the same patterns and do the same process as we did before. So we are going to start with the geometric series A1 times r, A1 times r squared, A1 times r cubed. Basically, this is right, A1 plus A2 plus A3 plus A4 plus all the terms up to A sub n, but we just don't know how many there are. So the first thing that we're going to do is write out our geometric series S sub n by using the equation for the single term, which remember that equation from before, a sub n is a sub 1 times r to the n minus 1 power. So S sub n is a sub 1 times r to the 1 minus 1 power, which is 0, plus a sub 1 times r to the 2 minus 1 power, which is 1, plus a sub 1 times r to the 3 minus 1 power, which is 2, plus dot, 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 all the way up to the nth term, which is going to be a1 times r to the n minus 1. So we don't know how many terms there are in between those two. That's why we have the dot, dot, dot. All right, step 1. Step 2 is multiply each term by r. Okay, we did this before. Now I'm going to multiply the whole equation by r. So we have r s sub n. Now, what happens when I multiply each one by r? Well, r to the 0 times r to the first, we add 1 to each exponent, right? Because we're multiplying by 1 more r. So here, a1, r to the 0 becomes r to the first, plus a1, r to the first times r to the first becomes r squared. All right, multiplying r squared by r, we get r cubed. All the way up to, now, this one. I am multiplying a sub 1 times r to the n minus 1. And let me actually do this over here. A little side note. When I multiply a1 r to the n minus 1 power times another r, remember I have these two bases, which I can condense them into one by adding their exponents. So n minus 1 plus 1. Well, what does n minus 1 plus 1 equal? Well, those ones cancel and it's just n. So what we get here is a1 times r to the nth power. Oops, that was the wrong color. That will bother me. All right. After this step, the next step is to subtract these two equations into one. So I'm going to subtract the second equation from the first equation. When I do that, each term becomes negative. And instead of rewriting it all out, I'm going to look for the terms that cancel. So we have s sub n minus r times s sub n. I see a sub 1 r to the first minus a1 r to the first. Those cancel. I've got a1 r squared minus a1 r squared. Those cancel. And if you remember when we did this, we had a whole bunch of canceling, right? Everything canceled except for the first term and the last term. So I know that we can't see what's in here because of these dot, dot, dots, but we know that as this pattern continues, every term cancels except for the first in the first and the last in the last. So we can assume that that happens here as well. we're left with a sub 1 times r to the 0 minus a sub 1 times r to the n. All right, next step after we subtract, so we've multiplied, we've subtracted, is to factor out. So we're going to factor out our GCF. On the left side, that's going to be s sub n, and I'm left with 1 minus r, equals on the right side, that's going to be a sub 1, and I'm left with r to the 0 minus r to the n. Also remember, simplifying as we go along, r to the 0, well, anything to the 0 power is just 1. All right, the next thing I want to do is divide by 1 minus r. I want to cancel out whatever's stuck with the s sub n so that I get it by itself. So I'll divide by 1 minus r. I'll do it to both sides. This cancels. I'm left with s sub n equals a sub 1 times 1 minus r to the n over 1 minus r. And look at that. That's exactly where we wanted to end up, right? Look at what we wanted and look at what we've got. You now are a mathematician.